You are watching the Unit 2, Lesson 6 video on Key Features of Functions, Day 2. One thing that you're going to notice with this lesson is there's a lot of repetition, but we're also going to be introducing some new concepts. Let's dive right into the very first problem. Given the function y is equal to f of x defined by the graph below, answer the following questions. A wants us to find the value of each of the following. F of 4. So f of 4 really means what is the y value when x is equal to 4? So if I move 1, 2, 3, 4 spaces to the right, I notice that I have to look up to positive 1 to get that value. So f of 4 is really 1. Next, I need to find f of negative 1. So when x is negative 1, what is my y value? So negative 1, and notice how I have to go up 1, 2, 3, 4, 5, 6 spaces. So f of negative 1 is positive 6. Part B says for what values of x does f of x, or y, equal negative 2? So when y is negative 2, well, that means I need to go 2 down. So 2 down. So 1, 2. And I'm going to draw a line where this is happening. Where is it hitting? Well, in 2 spots, here and there. What are those 2 x values? Well, that is x is equal to positive 1 because it's 1 to the right, and also x is equal to positive 3. And it says to illustrate on the graph. Looks like we've already done that. Yay! Taking a look at C now. State the minimum and maximum values of the function. Remember, minimum and maximum are y values. We can just write that off to the right. So the minimum is the lowest point on the graph, which happens right here. So how far down? Well, that's 1, 2, 3. So the minimum happens at negative 3. And the maximum, well, where's the maximum happening? The maximum is the highest point. And some of you might think that it might go to infinity, but remember, there are not any arrows on the end. So the highest point actually happens right there. So how high? Well, 1, 2, 3, 4, 5, 6. So the maximum is when y is 6. And lastly, for part D, it says to draw and label the axis of symmetry. So where can I draw a line that divides the graph into 2 equal parts? Well, that happens right here. And I know it doesn't say this, but I'm going to go a step further and actually give the equation of the axis of symmetry. If you look at this line, every single point on this line has the x coordinate of 2, whether it be 2, 0, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, or 2, negative 1, 2, negative 2, 2, negative, so on and so forth. The one common thing is the fact that the x value was always equal to 2. So my axis of symmetry is x. I'm just going to scribble that out. That got all messy. X is equal to positive 2. If we look at exercise 2, it's very similar to exercise number 1. So take a minute, pause the video, and answer part A. So here's the answers to A. Notice how you should get 1, negative 3, and 5 respectively. Moving on to B, it says, can the function rule given by the graph give you a value when x is equal to 5? And if so, what is it? And if not, why not? Well, I happen to think that this is a really interesting question. So let's look on our graph when x is equal to 5. So 1, 2, 3, 4, 5. It's right here. Now what happens when you look up and down to find the y value? Uh-oh, there isn't one. So can we really get a value? Can we get a y value for this? The answer is no. And if we are to explain, it's because the domain actually ends at 3. So let's write that out in words. So part B actually helps us with part C. It says, is x equal 5 in the domain of the function? Well, we just said that it was not. The graph doesn't go that far to the right, so the answer is no. Well, part D says, write the domain and range of this function using a single inequality. Well, we already wrote the domain in interval notation in part B, so let's translate that into inequality notation. So we are going from -5 is less than or equal to x is less than or equal to 3. Remember, our range works a little differently. So how low does this graph go? Well, the lowest point is right here. So that's 1, 2, 3, -4. And the highest point is not here. It actually is there. So 1, 2, 3, 4, 5. So -4 is less than or equal to, because it includes that point, y is less than or equal to 1, 2, 3, 4, 5. Continuing on to the next page, we have an exercise where we see 7 graphs below, and what we need to do is label each function, and then using our calculator, we're going to graph each of these functions and plot the table of values that you can see to the right of every single function. And the reason why we want to talk about parent functions is because these are the 7 main functions that we are going to work with this year. Are these all of the functions that can exist? No, there's many, many, many more. But in algebra, these are the 7 main types of functions, with the exception of piecewise and step functions, which we'll talk about later in the year. Without further ado, let's look at the first example, f of x, or y is equal to x. I'm hoping that many of you remember this from last year because you did a ton of work with lines in algebra. So this is what we call a linear function. So now let's take a minute to actually graph this or model this function on our calculator so we can see this table of values. Now it's going to depend on what you're using. Most of you are probably going to be using your iPad to do this. So in order to do that, you are going to hit New to create a new document, and we want a graph in this case. So we're going to graph it, and all we're going to type in after the f of x is just x. Then you can hit Enter. This line should appear. Now some of you might say, well, where do I get this table from? Well, in order to get that table of values, you're going to hit the wrench. It looks like a little wrench or a tool in the top left. And I don't know, about 6 or 7 words down, you're going to see the word table. And you're going to hit that and select the split screen table. Now it's going to work a little differently on your actual calculator in class because the app and the calculator aren't exactly the same, but I will definitely work with you on how to use them on your actual calculator. So hopefully you've been able to get a picture of this graph. So as you can see, when we look at that table, the x's and the y's are exactly the same. Or the f of x and the y's are exactly the same. Because, well, to be honest, it makes sense. The y is equal to the x, so I would hope that that's happening in this table. This is the point -2, -2, which lies right about there. -1, -1, 0, 0, 1, 1, 2, 2, 3, 3, and so on and so forth. I put in a -2, I get out a -2. This is where the table of values is coming from. So let's move on to the next function. It looks very similar to our linear function, but we have these little bars around it, which actually gives the function its name. This is an absolute value function. Now, the really cool part about an absolute value function is what it does is it takes the linear function, the negatives, and it reflects them over the x-axis and makes all of them positive, which makes sense because absolute value bars take the number inside and make it positive. It's the distance that number is away from 0. So if we create our table of values, well, we can first graph this doing the same strategy that I told you how to graph the linear function. But one way that we can also graph this is think about the input versus the output. Some of you might have the question, where on earth did you get these numbers from? And it's not like they're any special numbers. They're just numbers that I picked that I think would be nice to look at in terms of what we're looking at on the graph. I could have picked negative 100, negative 99, negative 9. I mean, I could pick any number that I really want and input it into the function. But we always will have a different output for every one of those inputs. That's why it's considered a function. So when I look at negative 2, if I take the absolute value of negative 2, that is just positive 2. If I take the absolute value of negative 1, that's just positive 1. If I take the absolute value of 0, still stays 0. And the absolute value of positive 1 is 1, and the absolute value of positive 2 is 2. So we can see all these points on the graph, negative 2, 2, negative 1, 1, 0, 0, 1, 1, 2, 2. And this absolute value function will always make a v. Continuing on to our next function, we now have f of x, or y, is equal to x squared. So our linear function now has a squared exponent, which creates what we call a parabola. We're going to do a lot of work with parabolas this year. They're also called quadratic functions. That's what we're going to label this one as. So this is a quadratic function. And remember, I talked about this a few days ago in class, but one thing that I notice a lot of people always make mistakes with is when they substitute in a negative and they square it, sometimes the signs are wrong. So let's just think about this one as we look at the table of values and graph this on our calculator. So if we graph this, we're going to notice that it makes a U shape. That's what a parabola or a quadratic function looks like. And we get that by taking every single one of the inputs, no matter what we put in, and squaring it. So what is negative 2 squared? Well, that's negative 2 times negative 2, which is positive 4, not negative. Same thing with negative 1. Negative 1 times negative 1 is positive 1. 0 times 0 is 0. 1 times 1 is 1. 2 times 2 is 4. Notice how whenever we multiply a negative times a negative, it makes it positive. That's why this part here is not down in quadrant 3. That's where the U comes from. And you can see all these points are actually on this graph. Negative 2, 4, negative 1, 1, 0, 0, and so on and so forth. Moving on to the next function, this is called a cubic function because of the exponent that's cubed. So take a minute, graph this cubic function on your calculator. Let's talk about what this cubing actually does to a number. So I'm going to experiment with my negative 2. Remember, I just picked these numbers because I thought they would be nice inputs so that way we could see a nice graph here. Oh, that looks terrible. That's supposed to be a 3. Let's fix that. So negative 2 cubed. All right. So what this actually means is that I'm taking negative 2 and I'm multiplying it by itself 3 times. So negative 2 times negative 2 is positive 4. Positive 4 times another negative 2 is negative 8. So I'm multiplying negative 2 times itself 3 times. Negative 2 times negative 2 times negative 2. Same thing with negative 1. Negative 1 times negative 1 times negative 1 is actually negative 1. 0 times 0 times 0, still 0. 1 times 1 times 1, still 1. 2 times 2 times 2, positive 8. So this is where that weird little curve is coming from. As you can see, it looks very similar to the quadratic function, except this piece here is now down below because of the way the cubic works. Because we do have negatives now. We can get negatives when we cube a number because we're multiplying a third negative to the product of two negatives, which is a positive. And a positive times a negative would give us these negative numbers here. That's why we're getting this part here. And also notice that it's getting a little bit steeper because we are multiplying a number times itself, not 2 times with the quadratic, but now 3. All right, 4 down, 3 more to go. So this one that we see here, this is called a square root function. Shocking, I know. And obviously it gets its name because there's a square root sign there. So one thing that I do want to correct in this table of values, actually, you know what? No, I don't want to correct anything. I like this table of values. One thing that we should notice, and if you have your calculator or even just a simple calculator, I want you to try to take the square root of negative 2. Hopefully when you do that, you get an error message. That's because we cannot take the square root of a negative. Well, not yet anyways. We will in Algebra 2, but until next time. So we're not going to write anything when we try to take the square root of a negative number. If we take the square root of 0, if we input a 0, we get a 0 out. If we take the square root of 1, we still get a 1 out. And the square root of 4 is just 2. Again, we've now made the connection with the point 0, 0, 1, 1, and 4, 2. And some of you might say, hey, why did you not do the square root of 3 and 4? Well, we could have, but is the square root of 3 and the square root of 4, are those going to give us nice integer values out? The answer is no, because they're not perfect squares. So I also probably would have picked like a number like 9 or 16 as an input, or 25. This is giving me this little square root function, and notice how there's nothing in the negatives because it's undefined there. The next function is called a cube root function. And it's called a cube root function because we're not taking the square root, we're taking the cube root. So what does that mean? Well, square root means we're finding two numbers multiplied by itself that will give us the number that's underneath here. Well, the same thing applies for the cube root, except we're not looking for two numbers, we're now looking for 3. Well, this is a little interesting. So let's take the cube root of negative 8. So what number times itself 3 times will give us negative 8? Well, that number is negative 2, because negative 2 times negative 2 is positive 4. And then if we multiply one more negative 2 times it, we get negative 8. Excuse the messiness. For some reason, my stylus is misbehaving today. So that's where we get that negative 2 from. If we take the square, or the cubed root rather, there should be a little 3 here, because otherwise it looks like a square root to me, and then we wouldn't have been able to answer this question yet. But if we take the cube root of negative 1, well, negative 1 times another negative 1 is actually negative 1. So the cube root of negative 1 is actually itself. The same thing with 0, the same thing with 1. But if we take the cube root of 8, and if you look at this table of values, you will see that the cube root of 8 is 2, because 2 times 2 times 2 is 8, not 6. And all of those points, of course, are on this graph. Negative 8, negative 2, negative 1, 0, 0, 1, 1. 8, 2. And it gives this weird little squiggle, but it's still a function nonetheless because every single value of x has its own value of y. And last but certainly not least is what we call an exponential function. And I know that some of you are really excited right now because you remember this from 8th grade. That's fantastic. So we are actually going to spend an entire unit talking about exponential functions, just like we did, or what we're going to do rather, with quadratics. They're one of the big ones that we talk about in algebra. So what does this mean? Well, the parent function is the most basic function, remember, that's what we're talking about here with all of these functions. This is the most basic type of each particular function. And then we can do some stuff with them, which we're going to get into later in the next few lessons. When we put in a -2 into our exponential function, so 2 to the -2 power, some of you might remember that that's really 1 over 2 to the positive second power. And 2 squared is really 4. This is really 1/4. So this is 0.25. I'm just going to write it as a decimal. 1/4 is 1/4, 25 cents. That's where I got that from. I could keep doing this, but typing this into your calculator, you'll be able to see all of this in your table of values, which I'm hoping that you're doing along with me. So this is 0.5. 2 to the 0 power, well, anything to the 0 power is always 1. 1, or really 2 to the first power, well, I only see 1, 2, so that's just 2. And lastly, 2 squared, 2 to the second power, is 2 times 2, which is 4. And if we look at the table of values, of course they appear. Notice how as we go farther and farther in the negative direction, my numbers keep getting tinier and tinier, which means that this line here actually goes on and on and on and on and on. It's kind of hard to see on this graph, but this keeps going, getting really close to the line y equals 0, but it will never ever touch. This is actually an asymptote happening right there. So that concludes the lesson. Let's do some more work on this during class.